An Introduction to Set Theory and to Philosophy and Methodology of Mathematics and Computer Programming by Jan Plaza. Section 1.5 Finite Sets. An overview. We define the notation such as this. And now I would like to ask a question. How many elements are there in this set? Compare your answer with this. If x1 is different from x2, capital X has 2 elements. If x1 equals to x2, X has 1 element. Here is an intuition we want to formulate at this point. If a set has n elements for some natural number n, we call the set finite. Otherwise, we call it infinite. This is just an intuition. This is not a formal mathematical definition. We will leave the formal mathematical definition of the concepts of finiteness and infinity for later. Axiom of pair and axiom of extensionality allowed us to write pair sets. These two axioms, together with other axioms of set theory, allow us to formulate any finite sets. And here is a definition. This symbol will denote the empty set, and it is defined by the condition such that X is a member of the empty set if and only if false. Right? The symbol I'm using here is the logical symbol for falsehood. So nothing belongs to the empty set. Now we'll use the notation like this to denote a set containing x1, x2, and x3. x1, x2, and x3 are separated by commas, and all of them are surrounded by curly braces. This is defined. This is the unique set Y, such that Y is a member of capital Y if and only if Y equals x1, or Y equals x2, or Y equals x3. In a similar way, we define a set containing x1, x2, x3, x4, And we can also define sets with 5, 6, and more elements. So this is going to be the notation we are going to use for finite sets. 5 is a member of the set containing 1, 5, and 7. 3 is not a member of this set. Why is this? Because 3 is different from 1, and 3 is different from 5, and 3 is different from 7. We can consider sets whose members are sets. So in this set I have 4 members. Here they are: the empty set, the singleton of 1, the singleton of 2, the pair of 1 and 2. And actually the conclusion that this set has 4 members depends on knowing that 1 is different from 2. So this has 4 members because 1 is different from 2. In the previous section, we discussed canonical forms. Could we develop a canonical form for writing finite sets of integers? What about representing a finite set of integers as a list of these integers in the strictly increasing order? You could implement a computer program which takes as input an arbitrary sequence of integers and produces the canonical form. In this way, it will be easy to compare whether 2 lists which could be entered represent the same set.